Welcome to Chapter 4.3, Distinguishing Among Atoms. In this first picture, we see several different types of dogs. And just like dogs come in different breeds, atoms come in different varieties. We're going to use atomic number and atomic mass number, or just mass number, to help us determine what makes one element different than another. So let's talk about atomic number first. Elements are different because they contain different numbers of protons. So let's take a look at this. So protons are what determines what element we have. So an element's atomic number is the number of protons in the nucleus of an atom. Okay? Now, that is a definition of atomic number. If we want to extend that, we'll see that in the neutral atom, we'll have the same number of electrons. But we'll learn later on in the year why the number of electrons is not the determiner of what element we have. So the atomic number is what gives the identity to the element. So if we change the number of protons, we have a different element. All right, so let's look at this chart. We have a mini periodic table here from hydrogen to neon, and we see the first 10 elements. So we see the atomic number increases 1 through 10, so that corresponds to the number of protons each of those elements have. Notice that they also increase from 1 to 10. So if you see these two numbers here, there's 1 and 1, 8 and 8, 10 and 10. So just as I said, the number of protons correspond to the atomic number. Now if you look over here, in a neutral atom, of course, we have the same number, 1 through 10. The mass number is different depending on the number of neutrons. For instance, hydrogen doesn't have any neutrons, so its mass number stays 1 because the proton has a mass number of 1. Helium has 2 neutrons, so its mass number is 4. So these must be related somehow, okay? And we'll give a definition of that shortly. So atomic number, as I said, we know that atomic number always tells us that we have a neutral atom. So the number of electrons equals the number of protons, because electrons are negative and protons are positive. So let's walk through with an example. If we start out with nitrogen, we have an atomic number of 7. So the number of protons should be, you got it, it should be 7. And if they're neutral, we should have 7 electrons. So there's a method, excuse me, that we use to get there. Okay, the atomic number gives us the number of protons. Oops. Okay, so if we know the number of protons, it will have to equal the number of electrons. So we use the atomic number to find the protons and electrons. So if we have 7, we have 7 protons, and therefore we have 7 electrons. Very simple. Now mass number, okay, a lot of you had this question when you were doing your element project, so it's a very, very simple term. Mass number is not atomic mass. We're going to talk more about atomic mass later on. So when we add the number of protons and neutrons together, this is called our mass number. So for instance, helium had atomic number of 2, or 2 protons. and 2 neutrons. So we add them together, so its mass number is 4. Okay? So if you know the atomic number and mass number of any atom of any element, you can determine the atom's composition, because from that you can tell what? You can tell the number of neutrons, because it's the difference between the mass number and the atomic number. So you've got neutrons. You subtract the atomic number from the mass number. That gives you neutrons. What does the atomic number give you? You should know that. So if you know the atomic number and the mass number, you can determine the atom's composition. So there's the calculation. Number of neutrons equals mass number minus atomic number. Also, you can also, once you know the atomic number, you know the number of protons and electrons. So let's look at how you can write that. Here's an example of gold. Usually when we write the mass number and the atomic number, it has a certain place in the chemical symbol. We write the chemical symbol, and to the left of the chemical symbol, we put the larger mass number on top and the smaller atomic number on bottom. This is very helpful when we want to find the number of neutrons, because we basically just say, what is 17 minus 9? That's going to be 8. And then 18 minus 7, it's going to be 7 minus 8 is 1, 118. So there's 118 neutrons in gold. So the neutrons make up a significant amount of the mass. Okay? So the atomic number is in the subscript, the lower number. The mass number is in the superscript. Okay, we can write our symbols 2 ways. We can write it the way we just saw, like this, or sometimes they spell the name out, put a hyphen, and the mass number. That will be a way of showing us the symbol. Okay, so you can see either way is acceptable. This is more of a shorthand. This is more of a longhand. All right, so now we're going to determine the protons, electrons, and neutrons of each atom. I'm going to walk you through this step by step. So we have beryllium, neon, and sodium. So beryllium, we have the larger number on top, smaller number on bottom. So this is our mass number, and this is our atomic number. Atomic number always tells us protons and electrons, so we get it right from there. If we subtract that from the mass number, we get the number of neutrons. And we're going to do the same for each one of the other ones. Let's look at the process more closely. So we write down what we know. We know the atomic number is 4. We know the mass number is 9. We know the atomic number is 10 for neon. Mass number is 20. Atomic number for sodium is 11. Mass number is 23. We want to know what the protons, electrons, and neutrons. Now this is a very important method when we're solving problems. These problems are kind of easy. We can do this on our own. But we have to very carefully look at these when we get to more complicated problems. So we're going to have our knowns and our unknowns. So let's continue on. So our atomic number, as I said, for the first one was 4, the second one was 10, and the third one was 11. That will tell us the number of protons because of definition. It will also tell us what? The number of electrons, right? So because they have to be the same in the neutral atom. So now we have to do a little bit of math to get neutrons. So we take our mass numbers and subtract the atomic number. So we end up with 5, 10, and 12 neutrons, respectively, for each of our atoms. So if we look at every atom, the mass number is equal to number of protons plus number of neutrons. And that makes sense because when we add up the neutrons and the protons, what do we get? We get our mass number. So what information is needed to determine the composition of a neutral atom of any element? We need the mass number and the atomic number. So the atomic number and the mass number are needed to determine the atom's composition. All right, so we need both of those. Now, isotopes. Isotopes, what are isotopes and how do we differentiate between isotopes of the same element? Let's think that through before we go on. If we know that the identity of an element has to do with its number of protons, which equals its number of electrons, what's the only part of the composition that can change to get an isotope? You think you got it? Let's see. Okay, here's neon. Neon has 3 isotopes. So I said the protons and electrons should be the same. Do you see that as true for each of the isotopes? Yes. Notice I have neon 20, 21, 22. That refers to mass numbers, the 20, 21, 22. Since the protons aren't changing, the only thing that can be changing is the neutrons. So neon 20, there's 10 of them, and neon 21, there's 11, and neon 22, there is 12. So if we look here, 10 neutrons, 11 neutrons, 12 neutrons. Add each of those to the 10 protons, and you get 20, 21, or 22. Okay? So there's a summary slide of what I just said. So, definition, isotopes. Isotopes are atoms that have the same number of protons but different numbers of neutrons. Okay, now that's really important that we say protons again instead of electrons. And I'm going to give you a little bit of a hint of why. Chemistry can be spelled E-L-E-C-T-R-O-N-S. You say, wait a second, Mr. Palladino, I didn't learn how to spell like that. Okay, but it really is all about the electrons. We are studying reactions of electrons. Electrons leave, they come, they go. Electrons are what really is what chemistry is about. So you can have the same number of protons and neutrons in an atom after it's gone through a reaction. So the isotope itself will remain the same even though it has different number of electrons because it's reacted. So that's why we don't mention the electrons here. Okay, so what I alluded to was that since there's different number of neutrons, and neutrons have the same mass as a proton, they're going to have different masses. So the difference between isotopes is they have different masses. And as I mentioned before, isotopes, this is really important, isotopes are chemically alike because they have identical number of protons and electrons in the neutral species. And that is what is responsible for the chemical behavior, as I hinted to previously. All right, so we saw the dogs before. They're still dogs. These 3 animals are dogs. They're just different isotopes, if you want to think of it that way. So isotopes are like different breeds of the same thing. Now, how are atoms of one element different from atoms of another element? And how are isotopes of the same element different? So let's answer the first question first. All right, so let's think about that. Okay, atoms of one element, what makes them different? Okay, it's their atomic number, right? So atomic number. So atomic number is the number of protons. Okay, how are isotopes of the same element different? So different masses. Or we could even say different mass number. And that's due to different number of neutrons. So let's see the long answer. Atoms of different elements are different because they contain different numbers of protons. Isotopes of the same element are different because they have different numbers of neutrons and thus different mass numbers. Okay? So my little note says all that paragraph in a much shorter way. So let's write the chemical symbols of isotopes. I showed you one, but usually when we do it, we actually do write it out in English. So for instance, we'll have carbon 12 and carbon 13. If I wanted to write that in symbol form, I'm going to use superscripts and subscripts. Okay, so basically isotopes are atoms that have the same number of protons. All right, so we know that means they have the same atomic number, but they have different numbers of neutrons. So that means their mass number will change. So the atomic number is the subscript, and mass number is superscript. So if we go back to the table previously, we'll see the symbol of carbon is C, and its atomic number is 6. So we are going to have a C, and we're going to have a 6 in the subscript so far. So let's write down what it's going to look like so far. So both of these are going to look like this to start with. Okay, but they have different mass numbers. And so this here tells us what the mass number. We don't even need to know the neutron because it was given in this name. So this would be carbon 13, and this would be carbon 12. So there we go. Why are atoms with different numbers of neutrons still considered to be the same element? Well, that's a great question. Okay, what did I say previously about what makes the atom, number one, the identity, and what governs the chemical properties? Well, the atomic number is the number of protons. That's going to tell you the identity. And how it reacts with other elements is the number of electrons it starts out with, which is the same number. The neutrons don't have a charge. They're in the nucleus, and they don't really react. So chemically, the isotopes are similar. They have identical numbers of protons and electrons, and this is what determines the chemical behavior. So how do you calculate the atomic mass of an element? Now, this is not mass number. Okay, some of you had this question when you were doing your element project. How do you calculate the atomic mass of an element? Okay, if we look at fluorine, which is it's not that big of an element, but one atom of fluorine has a mass in the order of 10 to the minus 23 grams. So that's 23 zeros before you put a number, grams. So a very, very teeny amount, okay? So very, very small numbers, which is kind of hard to work with all the time. So it provides useful information, but it's impractical math to use all the time. So we decided to give them values that were easier to use. So we use a reference isotope of carbon 12. So we use an isotope as a standard. So this is a very common concept in chemistry, the use of standards. We use something that we say, this is the value, and everything is relative to that. It makes math a lot easier for us to use, and it's still how things relate to each other, because what we saw in dimensional analysis, we saw how things relate to one another basically through ratios, okay? And that's really what we're saying here, is we're going to use something and then use our relative amounts based on that standard. So we created something called the atomic mass unit, which is a very, very teeny unit, which is basically 1/12 the mass of carbon-12. So 1 AMU is equal to 1/12 carbon-12 mass. Okay? So that's basically the definition of an AMU, which is when we're talking about single atoms. We will talk about something that makes this even easier when we get to the mole, but right now we're going to talk about AMUs when we're talking about little amounts of atoms. The nice thing is the numbers stay the same. So carbon-12 has 6 protons and 6 neutrons, right? Because it's C6. We just went over that earlier. So its mass is set at 12 AMU, or 12.00000 infinity, okay? That's our standard value. And almost all the mass is due to the protons and neutrons. Remember we said that an electron is 1/18/27 of a proton, so a very, very small amount. Little 12 electrons not going to change it too much. So a single proton or a single neutron is about 1/12 of an AMU, so it's about 1 AMU. So a neutron and proton both have a mass of approximately 1 AMU. Okay, in nature there's very, very few elements that do not have an isotope. They usually have at least one other isotope than the main isotope. Some have 3 or 4 or more. Okay, but each element has a fixed mass and a natural percent abundance. So I'm sorry, each isotope. So every isotope has its own mass because it has different number of neutrons, and it occurs in the same percentage all the time. So here we look at different elements. Hydrogen has 3 isotopes: hydrogen, deuterium, and tritium. Helium has 2, carbon has 2, oxygen has 3, chlorine has 2. So we look at each of their masses here, and we see 1, 2, 3, okay? Most of it is what we know as hydrogen is hydrogen 1. A little bit of it is hydrogen 2 or deuterium, and there's very little tritium, okay? But we notice if we look at the atomic mass, it's closer to the one that has the greatest abundance, okay? Helium is mostly helium-4, and there's a very, very trace amount of helium-3. So if you look at the atomic mass, it's going to be closer to the 4 because there's more of it. Carbon is mostly carbon-12 with about 1% carbon-13. So again, the atomic mass of carbon is very close to carbon-12. Oxygen is mostly oxygen-16 with a little bit of oxygen-17 and a little bit more compared to that of oxygen-18, but very, very trace amounts. And chlorine is a little bit different. Chlorine is 75% or so of chlorine-35, we call it, and chlorine-37, so it gets halfway in between. All right? Or closer to the 34.9 or 35. Okay? So here we have our chlorine example. So we have to know the natural percent of each of those, which we see on the table. So chlorine-35 is approximately 75%, so it's mostly chlorine-35 and only 24% chlorine-37. So what we have to do is we can't just add them up like this. Okay? We can't say, okay, well, we have two isotopes, we add them together, we get 2, and we end up with 35.986, but the value we actually get on the table is 35.453. Something isn't right. So we need to add them together. So what we do is we've got to take this into consideration here. So we have, if we have if we have 1, 2, 3, 75%, 25%. Okay? So all of them have the same number of protons. So that adds 68 units of mass. This has, 3 of them have 18 neutrons, and 1 has 20. That's 74 of mass. So we add those together and divide by 4, because we have 4 atoms, and we end up getting 35.5. So this is called a weighted average. Okay, this is called a weighted average. And that is how we determine atomic mass. That's why our atomic masses are all in decimal values. So the atomic mass of an element is a weighted average. Means that it's not simply add them all up and divide by the total number. You have to take the percentage of each amount. Okay? So it's a weighted average mass of the atoms in a naturally occurring sample of the element. A weighted average mass reflects both the mass and the relative abundance of the isotopes as they occur in nature. Okay, so you know an average is, that would be the mass itself, but it's also taking into account that they have different relative abundances. Okay, we can work backwards too from this. Okay, the atomic mass of copper is 63.546 AMUs. And we have two isotopes, copper 63 and copper 65. So which do you think is more abundant? Since this number is closer to 63, my bet is it's going to be copper 63. Let's see. The atomic mass of an element is the weighted average of the atoms in a naturally occurring sample. So that's our definition. So we compare the mass. Here's the actual atomic mass. Here's the mass number. We ask ourselves, as I said, which one is it closer to? Okay? Determine the most abundant isotope based on which atomic's mass is close to the atomic mass. And so it's a weighted average. Copper 63 must be more abundant than copper 65 because it's closer to it. Now, we also can calculate the actual atomic mass if we know the relative abundance of the different isotopes. So what do we have to do? We have to calculate the atomic mass by multiplying the mass of each isotope by its natural abundance. And it's going to be expressed as a decimal, and then you add all the products together. So let's see what that looks like. So here's carbon. We said it was mostly carbon 12 and a little bit of carbon 12, carbon 13. So we have 12 and 13. So we have 12 AMUs times 0.9889 plus 13.003 times 0.01111. So that's the masses times the relative abundances. We get two answers. We add them together, and we get 12.011 AMUs. Okay, that's how you do it. That's all that's to it. All right. So let's try one with element X. It has two isotopes. One has a mass of 10.012, that's X10, and X11 has a mass of 11.009. And it has a relative abundance of 80%. Before we do anything, it's mostly the X, so our answer should be closer to 80%. And we're going to calculate the atomic mass of element X. So here's our knowns. We know what the isotopes are, X10 and X11. We know the masses of each of them, respectively, and we know the relative abundance. We change the percentage to the decimal values, and now we're ready to do our math. So we just multiply. We get 1.993 and 8.817. We add those together, and we get our final answer of 10.810 AMUs. Does that make sense? If it's closer to the one that is smaller, let's look back there. It's closer to the one that is 11 versus the one that's 10. And it is. 10.8 is closer to 11 than it is to 10. So there we go. Why is the atomic mass of an element usually not a whole number? Well, because it's a calculated value based on a weighted average. Okay? Here are the summary concepts that we looked at. Might want to write that down in your notes. This is how we figure out the number of neutrons, mass number minus atomic number. Here's your definition. Stop the video. Write these down in your notebook. Same with these. Our big idea for this section was electrons and the structure of atoms. Atoms of the same element have the same number of protons, which is equal to an atom's atomic number. But atoms of the same element can have different number of neutrons. Atoms of the same element with different numbers of neutrons are called isotopes. And that's all we have today. Have a great day.